Okay, so what we're going to talk about is the half-life of a radioactive isotope. Half-life is the amount of time that it takes the remaining mass of a radioactive isotope to decay to 50% of its original mass. So for example, if we start out with 100 grams of a substance and we undergo one half-life, we will have 50 grams of that radioactive isotope and 50 grams of the stable daughter product. Now, remember, we talked about isotopes before, that they're heavier elements, that they have a larger atomic mass, and then they break down into a more stable. An example of one would be what? Carbon 14. Carbon 14 would then break down into nitrogen 14. So remember, half life is the amount of time required for the mass that you have to break down by 50%. So whatever mass you're left with, that breaks down by 50%. So we'll go through a couple of examples of this first. So first of all, you have your earth science reference tables, and it gives you the radioisotope here. And then you go and you have what it disintegrates into. Remember, this is the parent isotope, the carbon 14. This is the daughter product, the nitrogen 14, and that breaks down in one half-life of 5,700 years. Remember, with scientific notation, we move the decimal point 3 places to the right if it's a positive number, and you're going to add the appropriate zeros. So therefore, it would be 5,700 years for carbon 14. And this is the reason that carbon 14 is used for recent organic remains, because its half-life is so short. What do I mean by short? Well, let's look at uranium 238. Uranium 238, we talked about with zircon crystals, and that breaks down to lead 206. So uranium 238 decays to lead 206, and that takes 4.5 billion years, because that's 9 decimal places it's moved over. 9. So you're going to add 8 zeros to this. So it's 4.5 billion years. So this is what we're going to use for rocks, because when we talk about rocks, we're talking about millions and hundreds of millions of years ago with geologic history. So let's take an example of a Regents question of how this works. So what you have is the undecayed atoms are the shaded portion, and the decayed atoms are the white blocks. And what you have to imagine is you take a piece of paper like this here, and what you're going to have is you're going to have a piece of paper, and this is the carbon 14. After one half-life, this carbon 14 will break down into nitrogen 14. So it'll split that mass. Okay. You'll end up with nitrogen 14, the white, carbon 14 will be the shaded. Now look, it's half, so it's 50%. Now, after another half-life, this portion breaks down by 50%, and this is now carbon 14, and this is all nitrogen 14. Then this breaks down by half after one half-life, and you have carbon 14 and then nitrogen 14. So it breaking down the remaining mass. So the remaining mass is what breaks down. So if you take a look at this Regents question here, you'll see there are 8 blocks across the top, 4 blocks down. 8 times 4 is 32. So to start, there were 32 gray blocks. After one half-life, how many gray blocks would you have left? 16. So you'd have 16 gray blocks left, all right? And you'd have 16 white boxes. That's one half-life. If your radioisotope was carbon 14, how long would that take? Look at your earth science reference tables. That would be 5,700 years. 5,700 years. Then you take that remaining 16 gray blocks and you break that down by half. And how many boxes would you have? You'd have 8. So you'd have 8 boxes of carbon-14, and then you would have 16 plus 8, 24 boxes of nitrogen-14. Now take a look at this diagram and count them up. If you count up the gray boxes, you're going to count 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 gray boxes. So how many half-lives did this undergo? If we started with 32, after one half-life, you have 16. After another half-life, you have 8. So it underwent 2 half-lives. So you underwent 2 half-lives. Now you take this 2 and you multiply it by the half-life of carbon-14 on your reference tables, which is 5,700, and it gives you 11,400. So this sample would be 11,400 years old. Now what you do, all right, if you take a look at environmental factors, subject it to heat, subject it to pressure, subject it to water, pour lead over it. It does not change the half-life of the radioactive isotope. It stays the same. No matter what you do to it, the half-life does not change. Now, take a look at this box here. All right, here's an example. If we take carbon-14 is in the blue, nitrogen-14 is in the red, we take one half-life, 5,700 years, we end up with 50% of the carbon-14 left, 50% of the nitrogen-14. If we had 100 grams to start, we'd have 50 grams of each. Then after another half-life, you take that remaining blue. See, the remaining blue is what's cut in half. And then you have 25% of the original carbon-14 left and 75% of the nitrogen-14. And then you take that remaining blue after another half-life, cut it down, becomes 12.5% and 87.5%. One more half-life, 4 half-lives, you're going to end up with 0.625% and 88.125. And then one more box to be gone. But if you graph that chart, you take this chart right here on the right-hand side and you graph that, this is the kind of graph you're going to end up with. You're going to end up with a graph where the decay product, if we look at the decay product and we look at the parent isotope, the decay product is also known as the daughter product, right? So the mass of the original isotope is going to be the dark line because that's what's decreasing. And the mass of the daughter isotope is going to be the dashed line because that's what's increasing. So you're going to have the change in the radioactive isotope. Now notice where the two meet, where the two lines meet, it's one half-life. Why? Because this went down to 50% of the original mass, and this increased that same amount that we dropped down. And that's where you're going to have that 50-50. So therefore, that's your one half-life.